All right, so this is lecture 12 in our course, and we start the last chapter on eigenvalues and eigenvectors of matrices and linear transformation. This is in some sense the central topic of linear algebra. All applications of linear algebra, they have to do with eigenvalues and eigenvectors. And whatever preparation we have done so far in the course, it is to understand this chapter on eigenvalues and eigenvectors. We will study them for matrices and also for linear transformation. One has to understand both the concepts. Okay? So let us start. I want to first give a motivation for eigenvalues and eigenvectors, how they arise. First, of course, they arise in many applications: physics, engineering, and technology, computer science. They are everywhere. Every engineering branch needs eigenvalues and eigenvectors. But one of the places where first they arose first are while solving differential equations. So let us consider two ordinary differential equations. Ordinary differential equations are those which don't involve partial derivatives. Okay, we will consider differential equations with two two functions. Okay, these are coupled ordinary differential equations, dv over dt. Yeah, v and w are functions of t. They are differentiable functions of t, and the derivative of the first function is 4v minus 5w. Okay, derivative of the second function is 2v minus 3w. So they are coupled, just like linear equations in many variables are coupled equations. Here also we have two first order ordinary differential equations where two functions are involved, and we are given the values of these two functions at time t equal to 0. v0 is 8 and w0 is 5. And we want to solve for v and w. Okay. So initial values are prescribed. So we say it is a initial value problem. Okay. And the unknown functions are v and w. They are specified at t equal to 0. Initial values of v and w are specified. And we want to find v and w for every t. Okay. For every time in future, we want to understand how v and w are dependent on t. Okay. Now, obviously, we can write these in matrix form. This is the matrix form. Look at the column vector where the components are v and w. We can consider vector spaces of functions, right? We can consider vector space of functions. So I can consider this column vector whose first component is the function v and second component is w. And I regard this vector as ut. This is a vector of functions v and w. I write this as ut, and I can write derivative of this vector as derivative of each component. Just like position vector can be differentiated to give you velocity vector, and it has three components, and then acceleration vector can be gotten by differentiating the velocity vector, all the three components. Okay, so just like that, this vector of functions has derivative. The first derivative is obtained by taking derivative of vt and wt. Okay, and this function, this vector of functions has value 8, 5 at t equal to 0. So this is the ordinary vector in the plane, and that is the value of this vector of functions. And the matrix is 4, 2, minus 5, minus 3. These are the coefficients here of v and w. So if we set this notation, then the coupled equations can be written in matrix form. du over dt is au. Okay, where u equal to u0 at t equal to 0. Yeah, and so u0 is this, right? So we have converted these two coupled first order differential equations into a matrix equation. du over dt is au. U is a column vector. Here A is this matrix, and we want to find u at all times. Okay, so let us see how we are going to do this. So just like we have, suppose we have one differential equation of one variable and one function. It is not coupled. Du or dt is a u with u equal to u0 at t equal to 0. Then we know how to solve this equation. Ut is equal to e to the power at times u0. That is the solution of this equation. You just differentiate and check that it is equal to au. Okay, and u0, if you put t equal to 0 in this equation, t equal to 0 in this equation, e to the power at is 1, and so u0 is u0. This is checking. So for if you have one variable equation, differential equation of order 1, then the solution involves exponential function. This number a is going as a multiple of t, e to the power at u0. Okay. So one variable equation we know. Now we want to try similar solution for coupled equations. So let us say that Vt is equal to e to the power lambda t times y. So this is just copying this e to the power at. So I have put e to the power lambda t. Lambda is some number times a constant. Y is a constant. And Wt similarly is e to the power lambda t z, where z is some constant. And I have taken lambda equal. Okay. And we will see whether we can find out with equal lambda. Right. So we are just guessing here that the coupled equation may have similar solution, similar looking solution. So how to see whether these are solutions? Well, substitute v and w into the equation, vector equation. Ut is equal to e to the power lambda t x. Yeah, ut is this column vector. This is this column vector, and this is equal to e to the power lambda t times the column vector yz, and yz I'm calling as vector x. Y and z are constants. Okay, so therefore I'm writing this ut, which is a vector of functions, equal to this vector of functions where the first component is e to the power lambda t x, second y, and second component is e to the power lambda t times z. Okay, now we substitute this vt and wt into the differential equation. First differential equation, yeah. If you put it in first differential equation, du over dt, dv over dt is e to the power lambda t times y, and this is dv over dt. I mean dw over dt is lambda e to the power lambda t times z. Okay, and the right hand side, remember this was in terms of v and w with coefficients 4, -5, 2, -3. So I get these equations. But now you notice e to the power lambda t is present in every term here. And e to the power lambda t is never 0. So I can cancel. Yeah, e to the power lambda t can be cancelled. Once you cancel this, the rest are two equations in two unknowns. Yeah. So we get these two equations in two unknowns y and z. For lambda also we have to determine, right? But think of this as for a given lambda, the unknown quantities are y and z. And these two simultaneous linear equations can be solved, right? The coefficient matrix is invertible. So there is a unique solution in terms of y and z. Yeah. So, but this can be written as ax equal to lambda x. Remember, a is 4 minus 5 and 2 minus 3. X is the vector yz. Okay, and the right hand side is lambda y, lambda z. Okay, y and z are unknowns. So I have this matrix equation: a times this vector x is equal to lambda times x. Ax is equal to lambda x. Okay, x is a vector. X is a vector. So what is really going on? This matrix give rise to vector valued functions from R2 to R2. And here is my vector x. It is being mapped to a multiple of x. So lambda could be 0 or lambda could be non-zero. Yeah. So if lambda equal to 0, then every vector x is mapping to 0. Yeah. So ax will be equal to 0. But you see, A is a invertible matrix that will say x equal to 0, right? If lambda is not equal to 0, then I get that lambda x is not equal to 0. A non-zero vector is mapping to a non-zero vector lambda x. It's a multiple of x. Okay. So if I take E1, then it is mapping to lambda E1. If I take E2, it is mapping to lambda E2. If x was equal to E1, then E1 will be mapped to lambda E1. If x was E2, it will be mapped to lambda E2. So the line which is passing through x is mapped to the line which is passing through x under the action of A. Yeah. So if I take line passing through x and the origin, it is mapped to itself under the action of A. Take the linear transformation TA from R2 to R2, and this TA maps this line L to the same line L. Okay. Yeah. So the matrix A gives rise to a linear transformation from R2 to R2. That linear transformation is mapping a line to itself. Okay, that is the meaning of AX equal to lambda x. So that is the equation we get. Okay. Now this is the fundamental equation for this chapter. Yeah, to find out all lambda and all x so that AX equal to lambda x. And once we solve this equation, then we go back and substitute into this equation, and we can solve the system of differential equations. Right? Y and z can be found, lambda can be found. Okay. So let us approach this general problem. Think about when is it possible that there is a vector x so that AX equal to lambda x. This is not always true. Yeah? You may not be able to find an x which is mapped to lambda x. We will see an example very soon. Okay. But in many situations, you can find lines which are mapped to the same line. And the vectors which are along those lines, these vectors along these lines, these are non-zero vectors. They are called eigenvectors, and lambda is called eigenvalue. This lambda is the scaling coefficient. Yeah, the vector x is scaled to lambda x, and lambda is the scaling factor. So scaling factor is called the eigenvalue, and this vector x is called eigenvector of A. Okay, but so whenever you have a n by n matrix, we can consider complex matrices, real matrices, or matrices over field of rational numbers. And suppose I have a lambda which is in the same field of scalars, yeah, and an x which is a vector, so that AX equal to lambda x. Then we say lambda is an eigenvalue of this matrix, and x is an eigenvector corresponding to the eigenvalue lambda. Okay. So x has to be a non-zero vector. That is a precondition, and lambda is any complex number. So if AX equal to lambda x, where lambda is some complex number and x is a non-zero vector, then we say lambda is an eigenvalue and x is an eigenvector. Okay. A lot of time nowadays goes into finding eigenvalues and eigenvectors. Okay. So you can read an essay on internet. What are the applications of eigenvalues for Google search? Whenever you do Google search, you are actually computing some eigenvalues. The system is computing eigenvalues in order to tell you which are the most useful web pages for your Google search. So there is a listing. Yeah, as soon as you search a word in Google, Google will give you a list of web pages, and that list is in descending order of usefulness. If you go down the list quite deep, you may find absolutely no useful information. So what Google does, it searches through billions of web pages, and it will give you a list of useful web pages. This is done by computing eigenvalues. Okay, I'll give a link to an essay which explains how Google search is done. This is a modern application. Yeah? But eigenvalues and eigenvectors, they have been used in all applications of mathematics to technology and engineering in many contexts. And solving differential equation is one of the major applications of eigenvalues and eigenvectors, and you will see this in next course. Okay, in 108, you will see many situations where eigenvalues and eigenvectors are used to solve differential equations. And in general, whenever some phenomenon is modeled by mathematical equations, we come across a system of differential equations. And in order to gain insight into the physical model, we have to solve the differential equations. But solving differential equations is a rather tedious task. So in practice, they will set up the differential equations, but they will linearize the differential equations and reduce the problem of solving differential equations to a system of linear equations, just like we did here. This is a system of linear equations. It came from solving two differential equations in two functions. Yeah, we did this transformation. Yeah, we guessed the solutions and we reduced the problem to finding an x so that ax equal to lambda x. So the problem of finding solutions of these two differential equations is reduced to the problem of finding eigenvectors and eigenvalues of the coefficient matrix. This happens all the time in applications of linear algebra, that we have to compute eigenvalues and eigenvectors. Yeah. So if ax equal to lambda x, I can write this system of linear equations and convert into a system of homogeneous linear equations by having the coefficient matrix as A minus lambda times identity times x. Yeah, lambda is some value we have to find, and then we have to find the eigenvector. So it's in a sense, it is not really a linear algebra problem. It's a non-linear algebra, because this is lambda is unknown and y is unknown. So this is a quadratic. This is a quadratic. Yeah. But we fix lambda, then it's a linear algebra problem. It is we can find out the solutions in terms of lambda. So first we convert this equation into this system of homogeneous linear equations, A minus lambda I x equal to 0. Yeah, and we know when a system of homogeneous linear equation has a solution, non-trivial solution, we are looking for a non-zero vector. X is eigenvector is always a non-zero vector. So if A minus lambda I times x is 0, where x is non-zero, then we have understood before that A minus lambda I is not invertible. Invertible matrices, if I have an invertible matrix and I have a system of homogeneous linear equations, then this says that x equal to 0 because I can multiply by B inverse. So if we want a non-zero x, then A minus lambda I is not invertible, and therefore its determinant is 0. Yeah, its determinant is 0. So x is a vector in the null space of A minus lambda x, because A minus lambda I times x is 0. Okay, so A minus lambda I is a singular matrix, and so its determinant is 0. Once determinant of A minus lambda I is 0, A minus I is a singular matrix, and therefore we can find some x in the null space. So in order to find eigenvectors and eigenvalues, we can just look at this equation, determinant of A minus lambda I. Okay, this is a polynomial in lambda of degree equal to the order of this matrix. Suppose A was this 2 by 2 matrix. Yeah, A is a 2 by 2 matrix. Let us say 1, 2, 3, 4, and then I take lambda times I. Okay, that is equal to 1 minus lambda, 2, 3, 4 minus lambda, and take its determinant. So 1 minus lambda times 4 minus lambda minus 6 equal to 0. So I get lambda square, and then minus 4 lambda minus 5 plus 4 minus 6. So lambda square minus 5 lambda minus 2 equal to 0. So I get a quadratic equation in lambda. Yeah, its solution may be real, they may be complex. Lambda may turn out to be complex. Even if the matrix A is a real matrix, lambda may turn out to be complex, because lambda for the case of 2 by 2 matrix, lambda is turning out to be a root of a quadratic equation, and a quadratic equation can have complex roots. Yeah. So this lambda, which we want to call eigenvalue, right? It may turn out to be complex, but there is a restriction. When we say lambda is an eigenvalue and A is the matrix and X is the eigenvector, our field of scalars have to be fixed beforehand. We can't change in the course of our discussion. We cannot change the field of scalars. So you want to remain within the world of real matrices, and suppose lambda turns out to be complex always, then A will have no eigenvalue. You regard A as a complex matrix, then lambda is an eigenvalue. So every 2 by 2 complex matrix, here this calculation shows every 2 by 2 complex matrix has a eigenvalue and it may be a complex number. Okay, yeah. So lambda is an eigenvalue of A if and only if determinant of A minus lambda I equal to 0. And so this polynomial of degree n, if A is a n by n matrix, determinant of A minus lambda I, this is a polynomial of degree n. This is called the characteristic polynomial. Okay. So every matrix A has a characteristic polynomial associated with it, and the degree of this polynomial is equal to order of the matrix. If my matrix is n by n, determinant of A minus lambda I is a polynomial in lambda of degree n. Okay, and in our case, this is the characteristic polynomial, determinant of A minus lambda I, and the roots in this case, fortunately, are lambda equal to -1 and lambda equal to 2. Okay, so this says that for lambda equal to -1 and lambda equal to 2, Ax equal to lambda x has a solution. So these are the scaling factors. Yeah, these are the scaling factors. If x is mapped to lambda x, the entire line which is passing through x and the origin is also mapped to the same line. But there is a scaling factor lambda. So the characteristic polynomial, the roots of the characteristic polynomial tell you that there are only finitely many scaling factors possible. You can't, the scaling factor cannot be arbitrary. Lambda cannot be arbitrary. It is a root of a degree n polynomial if A is a n by n matrix. And there is a fundamental theorem of algebra which says that if I have a polynomial of degree n with complex coefficients, then it has n roots counted with multiplicity. Okay, so eigenvalues are roots of the characteristic polynomial, and for each eigenvalue I can find out the corresponding eigenvector. So put lambda equal to -1, then I have to solve Ax equal to -x. Take lambda equal to 2, I have to solve Ax equal to 2x. These are homogeneous equations. Convert them into homogeneous equation, use Gauss elimination, and find out the values of x which are possible. So you will find all possible vectors x so that lambda is -1. Second equation, if you solve, find out all x so that Ax equal to lambda x. So these x's, they form a subspace. So lambda equal to -1 leads to this system of linear equations.